Welcome back. So today we're going to look at one last randomized algorithm. And this algorithm is used to solve linear programming. So linear programming is actually a very important problem in computer science, in mathematics, operations research, and it's actually used in many fields. Okay, so I'm first of all going to introduce the problem to you guys, and then we'll talk about a randomized algorithm to solve linear programming problems. And then lastly, I'll give you some background about linear programming, and then I'll tell you about some applications for linear programming. Okay, so to introduce linear programming, suppose we have the following problem. Okay, so suppose there's a farmer and he's got some land. So he's got 100 acres of land. And on this land, he can either plant wheat or barley or both wheat and barley. Okay, and so now the farmer wants to make as much money as possible by planting wheat or barley. However, he's subject to some constraints in terms of how much wheat and barley he can plant. Okay, so first of all, the total amount of wheat and barley, the land that he uses for both wheat and barley, can add up to at most 100, right? Because that's the amount of land that he has. And also, suppose the farmer only has, let's say, 420 kilograms of fertilizer, okay? And he's got 160 kilograms of pesticide. And now, when he plants these things, he needs to use both fertilizer and pesticide. Okay, now suppose that for each acre of barley that he plants, he needs to use 5 kilograms of fertilizer and then 1 kilogram of pesticide. And then for each acre of wheat, he needs to use 3 kilograms of fertilizer and 2 kilograms of pesticide. And now the farmer is trying to plant the stuff so that he can sell it. And so suppose that the wheat is going to sell for $3 per acre, okay? And the barley is going to sell for $4 per acre. Now, in reality, of course, wheat and barley are going to sell for a lot more than that, okay? But so we're just choosing these two numbers for simplicity. Okay, so then the question is, how many acres of wheat and barley should the farmer plant in order to maximize his income? Okay, remember that he's going to make $3 per acre of wheat and $4 per acre of barley. Okay, so then to figure this out, let's let W and then B denote the number of acres of wheat and barley that the farmer is going to plant. Okay, so then since he's going to make $3 per acre of wheat and 4 per acre of barley, then the farmer basically wants to maximize this function 3W plus 4 times B. Okay, but when he does this, he's also subject to all of these constraints that we talked about above. So for example, he's only got 100 acres of land, and then he's only got so much fertilizer and pesticide. Okay, so then let's try to understand these constraints a bit better. Okay, so now we're going to summarize all of these constraints using these equations over here. So the farmer is trying to maximize his profit, right, or his revenue rather, okay, so, which is equal to 3 times W plus 4 times B. Okay. However, he is subject to these constraints where the acres of wheat plus the acres of barley can add up to at most 100, right? That's how much land the farmer has. And then also for each acre of wheat, he needs to use 3 kilograms of fertilizer, okay? And then for each acre of barley, he needs to use 5 kilograms of fertilizer. So therefore, if he's going to plant, W acres of wheat and B acres of barley, then we need that 3W plus 5B is going to be less than the total amount of fertilizer that he has, which is 420. Okay, and likewise, for each acre of wheat, he needs to use 2 kilos of pesticide and 1 kilogram of for each acre of barley. And so this 2W plus B needs to add up to no more than the total amount of pesticide that he has. Okay, so then we have these inequalities which constrain what the farmer can do. Okay, so let's try to understand these inequalities a bit better. So now since we only have two variables, W and B, okay, we can actually try to understand these inequalities by plotting them. Okay, by making a two-dimensional plot. So for example, if we want to look at the land constraint, okay, then we can make a two-dimensional plot where one of the dimensions is wheat and the other one is barley. Okay, so let's say that this vertical one here is going to be wheat, and then this one is going to be barley over here. Okay, and then we need to make sure that W plus B is at most 100. Okay, so if you plot that, then this is going to correspond to this blue area in the plane. Okay, so you see that this blue area is characterized by this line, which is W plus B exactly equals 100. Okay, and then everything beneath that line, we have W plus B is less than or equal to 100. Okay, so that's just for the land constraint. Okay, and now if we just look at the fertilizer constraint, then we need to satisfy, so again, we're going to make a 2D plot where we're going to make the vertical axis the wheat axis, and then the horizontal one is going to be B here. And so now we need to satisfy this inequality 3W plus 5B is less than 420. Okay, and if you plot this out, you're going to see that it corresponds to this shape over here. Okay, so actually I'm cutting off part of the shape. Okay, so this figure would actually would keep going, would extend further. Okay, but anyway, so part of this is actually cut off. Okay. So now, so when the farmer, is deciding how much stuff to plant, he's actually subject to both of these constraints. Okay, so we actually need to combine both of these constraints. And when you combine them, so what you can do is you can just overlay the two constraints. Okay, and then what you see is that there are some points which satisfy one constraint, but does not satisfy the other constraint. Okay, so then for those points, we actually need to eliminate those points because we need to satisfy all the constraints. Okay, so for example, this point over here. Okay, so this point satisfies the fertilizer constraint, right? Because it's in this pink region. Okay, but it violates the land constraint because it's outside of the blue region. Okay, and likewise, this point over here, it satisfies the land constraint but violates the fertilizer constraint. Okay, so we need to actually remove both of these points. And in fact, we actually need to remove all of these points in this sort of triangular region over here, and also all the points in the triangular region over here. Okay, because all of those points violate either the land or fertilizer constraint. Okay, so then what we want to do is basically take the intersection of the land and fertilizer regions, okay, the blue and the pink region. And then when you do that, you're going to end up with this, purple thing over here, okay? All right, so this purple region represents all the points which satisfy both the land and the fertilizer constraints. Okay, but we're not done yet because we have one more constraint, which is the pesticide constraint. Okay, so we're going to take our this region for the land and fertilizer constraint, and then we need to add on top of it this pesticide constraint. Okay, so the pesticide constraint, if you plot it, then again, it's going to correspond to a region in the plane. Okay, so this region again is going to extend out farther. Okay, but I'm showing just part of this region. And then so then we need to satisfy all three of these constraints: the land, fertilizer, and pesticide constraint. So that means that we need to take the pesticide constraint and then intersect it with the land and fertilizer constraints. Okay, so we need to take this green region here and then intersect it with this purple region over here. And when you do that, you're going to find that you end up with this yellow region over here. Okay, so this yellow region contains all the points which satisfy all three constraints. Okay, so now we know what are the points which satisfy these constraints. Okay, so then the next question is, out of all of these satisfying points, which one is going to help us maximize this, this revenue for the farmer, this 3W plus 4B function? Okay, now to understand that, what we're going to look at is we're going to look at these things called level sets. Okay, so these level sets are basically, well, we're going to take this function which gives the revenue, and we're going to look at all of the points which give the same amount of revenue. Okay, so for example, this line over here, the bottom red line, okay, this is a set of all points such that 3w plus 4b equals, is this correct? Equals 30. Is this correct? Okay, so I think these lines are off by a little bit. I mean, these numbers are off by a little bit. Okay. However, the point is that this this red line over here. Let's see. So this was the vertical axis was supposed to be wheat, right? Yeah, I guess. So okay. So, anyways, this red line over here, okay, so the scale on the axis is off by a little bit, okay, but the basic point is that this bottom red line corresponds to all of the points such that 3w plus 4b equals a constant value, okay, so it might not actually be 30, but anyways, if we fix this this value here, this on the right hand side to be a constant, then the set of all points which where 3w plus 4b equals that constant is going to be a straight line. Okay. And now if we take if we change this constant, so if you change it to 50, right? Then if you look for all the points 3w plus 4b equals 50, that's also going to be a straight line. Okay. However, it's going to be shifted from the previous straight line where 3w plus 4b equals 30. Okay, so it's going to be shifted upwards in this direction. Okay, and then if you change the 50 to a 70, right, and then again the set of points that satisfy, this equation over here is going to be a straight line that's again shifted from the line for 3w plus 4b equals 50. Okay, so what this is showing is that now these numbers here, the 30, 50, 70, and so on, this represents the amount of revenue that the farmer is getting, right, for different combinations of W and B. Okay, and what this is showing is that if you move these lines in the towards in the upward right direction, right, then you're going to be making more and more revenue. And so since what we want to do is we want to look at all of these W and B combinations that the farmer is allowed to do, and that's given by this yellow region over here. And then in this yellow region, we want to maximize the revenue as much as possible. Okay, so then what you want to do is you want to take these lines. So now, by the way, these lines are all parallel to each other, right? Yeah, the slopes of all of these lines are the same because we never changed this equation over here. Or sorry, the left-hand side over here. Okay, so all these lines are parallel to each other. And so then what we want to do is just take one of these lines and then shift it upwards and to the right. And then we want to keep doing that until we get to the boundary of the of this yellow region over here. Okay, because once you get to the boundary of this yellow region, then you can't push this line upwards anymore. Because if you push this line upwards some more, right, if you push it up to, let's say, this line over here, then none of the points on this line actually satisfy these constraints anymore. Okay, they're outside of this yellow region now. Okay, so you want to push this line upwards as much as possible because as you push it upwards, right, you see that we're making more and more money over here. Okay, however, you can only push it up until the while this line still intersects the yellow region. Okay. So then you see that the farthest side you can actually push this line is to this this one over here. Okay, and then when you push it up to that point, you're going to find that this line is going to intersect this yellow region at a point where W equals 40 and then B equals 60. Okay, so that and then when this happens, then your revenue is actually going to be 360. Okay, and then this point, you see that it actually intersects the yellow region, so it satisfies all these constraints. Okay, and this is also maximizing the revenue for the farmer because, as we said, we want to push this line upwards as much as possible, right? So, for example, this line over here is better than this line, okay? Because this line over here is going to make less money. Okay, so this top line is better than the bottom line, but you can't push this top line out any farther because if you do that, then you won't satisfy the constraints anymore. Okay. Yeah. So okay. So now let's sort of summarize all the stuff that we just talked about. Okay. Now, first of all, this yellow region. Okay. This yellow region corresponds to where all of the constraints are satisfied. Okay. We're going to call this the feasible region of the linear programming problem. And now the key fact is that this optimum point that we're trying to find, the one that maximizes the revenue for the farmer, okay, this is going to lie at one of the corner points of the feasible region. Okay, so you notice that the feasible region, so let's go back to this picture because it's a bit easier to see, right? The feasible region is made up of a bunch of straight lines, okay? And there are some corner points where, two of these lines are going to meet, and then the slope of the feasible region is going to change. Okay, so for example, here we have one of these corner points. And then here we have one of these corner points. Okay, we have a corner point here, and then we have a corner point here. Okay, so the corner points were formed by these intersections between the individual constraints, right? So for example, when we took the land constraint and the fertilizer constraint together, right, then when you intersect them, you're going to create one of these corner points. Okay, and then when you intersect this with the pesticide constraint, you're going to create another one of these corner points. Okay, and we're going to call these corner points extreme points. And what we saw, by this reasoning over here, was that the optimum value is going to lie at one of these extreme points. Okay, because we want to push this red line up as much as possible, right? And then this is going to so that's going to correspond to one of these extreme points. Because here, once before you hit this extreme point, you can keep pushing this line upwards. And then after you hit this extreme point, you can't push the line out any farther because then you'll be violating some of the constraints. You'll be outside the yellow region. And so therefore, the optimum is going to lie at one of these extreme points. Right, and then the procedure for actually finding the optimum is to take now these lines were formed by taking the objective function, which is this function 3w plus 4b, right? And then all of these red lines are perpendicular to that objective function's direction, right? And then we were pushing these red lines until they they hit one of the extreme points of the feasible region. Now, these extreme points are, where do they come from? Well, they come from the intersection of two constraints, as we saw earlier, right? And then, so these two constraints which form each of these extreme points. Okay, so each extreme point is formed by possibly two different constraints. Okay, so like this blue one over here was formed by I don't know, like the land and the fertilizer constraint. Okay, and then this one over here was formed by the land, what do we have here? The pesticide and fertilizer constraint. Okay, so so each of these extreme points is formed by some of these constraints. Okay, and in fact, since we're in 2D, right, then each of these extreme points is formed by the intersection of two constraints. And so we're going to call these constraints the basis of this extreme point. And then what we know is that the optimum is going to lie at an extreme point, and so the optimum is going to lie at the intersection of two constraints. Okay, and right, so we're going to call this these two constraints the basis for the optimum. Okay, now it is possible that some of these points are formed by the intersection of three constraints. Okay. However, because we're only working with two variables, then in general we can just assume that each of these extreme points is only the intersection of two constraints. Okay, so we're gonna make this sort of this general position assumption that none of these optimum are the intersection of three different constraints. Okay, so each of these is formed by the intersection of two constraints. Okay, so now we're going to get to a randomized algorithm. So we're trying to figure out what the optimum point is, right? And so now we're going to see a randomized algorithm for finding these optimal points. For example, for finding this blue point over here. Okay, and one of the observations in this algorithm is that since the optimum is defined by two constraints, right? So that's what we said. Then we actually have many constraints, right? We could have, so here we have 3 constraints in total, but we could have added more constraints, right? We could have had 100 constraints, okay? But even with 100 constraints, each of these extreme points is only going to be formed by the intersection of 2 of these constraints, okay? So that means that even if we had 100 constraints, you know, so the optimum, which is like over here, right? This is formed by 2 of these constraints. So that means that the other 98 constraints are actually redundant. Okay, they're not useful, meaning that we can actually remove those constraints and it would not change the optimum, right? So for example, if we removed this constraint over here, okay, this would not change the fact that you know, this point over here is the optimum for the for this problem. Okay, so we could have actually removed the oh, sorry. So this is okay. So this point is formed by the I guess the pesticide constraint, right? And then the which one is it? The land constraint. Yeah, is it? No, it's not the land constraint. It's the okay. So it's a pesticide constraint and the it is a land constraint. Okay. So then here you have the pesticide constraint, right? And then here you have the land constraint. Okay. So it's actually formed by these 2 constraints. So we could have actually removed the fertilizer constraint, and that would not change this extreme point over here. Okay, right? We can actually take this fertilizer constraint out. Okay, this fertilizer constraint. This is the fertilizer constraint. Okay, so that's one of the main observations here. That because the optimum is defined by 2 constraints, then we can actually remove the other constraints. So they're redundant. Okay, so for example, you know, here, if we look at this figure here, then what this is trying to show is, so now remember that in 2D, these constraints are given by these half planes, right? So basically we draw a straight line and then we look at, you know, 1/2 of that straight line, okay? And those points are all the ones which satisfy one particular constraint. Okay, so now these lines over here represent a bunch of these half planes. Okay, so for example, this line over here says that we need to, so we're allowed to consider any point which is on the right-hand side of this line. Okay, so that's what the purple over here represents. So we can consider any point sort of in this region. Okay, and likewise, you know, this line over here, right? This says that we can consider any point which is like beneath this red, black line. Okay, so any point over here, right? And then this line over here, right? So here the purple region points up. So that means that we're allowed to consider anything which is above this line. Okay. All right. And now for this problem, suppose that our objective direction. So remember that in order to get to the optimum, we want to move a certain line in a direction. Okay. So we want to consider, like, you know, these straight lines which are perpendicular to this optimizing direction here. Okay, so now our optimizing direction is pointing straight up. Okay, so that's what the C vector is. And so now you can see that in order to satisfy all these constraints, okay, so we have 5 constraints over here. So in order to satisfy all these constraints, this star here is actually the point which satisfies all the constraints. Okay, so for example, you know, this point over here, okay, we can't use this point because it violates this constraint. Right, because it's not to the, we need to be to the left of this line, and this is to the right of that line. Okay, yeah. So the point which optimizes this objective direction is going to be this red star point over here. Okay, so we're going to say that a constraint is tight if the optimum lies on its defining line. Okay, so here the optimum is this red point, right? And the two tight constraints are the ones where you know, this point actually lies on that constraint's line. So that would be this constraint and that constraint. Okay, yeah. So these two are tight. And then the other ones are redundant. Okay, so because for all of the other constraints, we can actually take them out, and it does not affect the optimum. Okay, so for example, if you just took out this constraint, okay, well then this point is still this red star here is still the point which optimizes in the C direction. Okay, right? Because we need to be, we need to be beneath this line and then also beneath this line. And so the, the highest point, which is beneath both of these tight constraints, is going to be this red line. Okay, these redundant constraints actually, are not going to change the optimum at all. Okay, so now suppose you have a 2D linear program. Okay, so 2D means that we have two variables, like wheat and barley. Okay, and now suppose it's got n constraints. Okay, so previously we had 3 constraints, but now let's say that you have a lot of constraints. You have n constraints. Okay, now what we know is that the optimum is defined by 2 of these constraints. Okay, and so that means that all of the other n minus 2 constraints are redundant. Okay, and so so therefore, if you pick a random constraint out of these n constraints, there's only a 2 in n probability that it's one of these tight constraints that defines the optimum. Okay, and if the constraint is not tight, right, then it's going to be redundant. And we saw that even if you take out the redundant constraint, it's not going to change the optimum. Okay, so this gives us a way to tell whether a constraint is tight or not. Okay, so if I give you one of these constraints, right, so here there are 5 constraints, and I ask you whether it's tight, okay? So the way we can do this is that suppose that we have a set of constraints, okay? Let's call that G. Okay, so here, for example, we have 5 constraints in G, okay? And now let's let B of G be the optimum value of the objective function subject to these constraints. Okay, so that's this red star here. Okay, then we can say that a constraint H, okay, this is going to be redundant if the optimum value for when you have, so let's let this constraint little h come out of this large set of constraints, capital H. Okay, then if you look at the optimum for this large set of constraints, capital H, and then you compare it to the optimum for the constraints capital H, but then you take out this little h constraint. Okay, and if these two values are the same, then this tells you that H is redundant. Okay, so as an example, so here we have 5 constraints. Okay, and so suppose that this is our little h over here. Okay, now we know that initially, if we look at all 5 constraints, the optimum is at the star value. Okay, and now if you look at even if you take out h, okay, so then you're just left with these 4 other constraints. We saw that the optimum is still going to be at the star value. Okay, so that means that b of h equals this b of h, capital H minus little h, and that tells us that little h is actually redundant. Okay, yeah, so this is a way to tell whether a constraint is redundant or not, and then that also tells us, so if it's not redundant, then it's tight. Okay, and if it's tight, then we know that the optimum is actually going to lie on one of these tight constraints, right? Okay, so now that we have this, we can actually develop a randomized algorithm for solving these 2-dimensional linear programs. Okay, so for example, so what we're going to do is, so H is going to be our set of constraints. Okay, and if there are only 2 constraints, right, then these 2 constraints are going to intersect at a single point and a single extreme point, and we know the optimum is at an extreme point. Okay, so therefore we're just going to output the intersection of these 2 constraints. Okay, so then otherwise we have more than 2 constraints. So then what we're going to do is we're going to pick a random constraint out of the set capital H. And then we're going to find the optimum value when we take this little h out. Okay, so we're going to look for, so we're going to form the set of constraints capital H minus little h, and we're going to find the optimum value, which is this b thing over here. Okay, and the way we can do this is that So this again is going to be, this thing here is also a linear programming problem. So we can actually recursively look for this optimum. Okay, so now suppose we've found this optimum. Okay, then we're going to check if the optimum doesn't violate h. Okay, then we're going to output that optimum. So for example, here we have this we have this optimum over. So if we pick h to be this constraint over here, then we have this optimum over here. And when you take h out, and then you look for the optimum without this h, okay, the optimum is still going to be at this star over here. And so now notice that this star does not violate h. Okay, h just says that all these feasible points need to be below h. And this red star here is indeed below h. So it does not violate h. Okay? And so in that case, what we know is that h is actually a redundant constraint. Okay, because the optimum doesn't violate h. And because it's redundant, because h is redundant, then it doesn't affect the output. The optimum. Okay, so that means that when h is redundant, then this b of capital H minus little h is equal to b of capital H. Okay, and this b of capital H is what we're trying to find. And so therefore we can simply output this value as the optimum. Okay, now the other case is where this optimum actually does violate h. Okay, so in that case, what we're going to do is we're going to project all of these other constraints onto h's boundary. And then this is going to produce a one-dimensional LP. So we start with a two-dimensional LP, and this projection is going to produce a one-dimensional LP. Okay, so I'm going to show you what this projection means and what all of these terms like projection and boundary, I'll show you on the next page what they mean. Okay, but the point is that we're going to project all of these constraints onto h's boundary. This is going to produce a one-dimensional LP, and then we can just directly compute the optimum of the one-dimensional LP. Okay, and I'll show you why we can do that on the next page. All right, but this is the algorithm for the 2D LP. Okay, we're going to pick a random constraint. We're going to find the optimum when you take out that constraint. And then if that optimum does not violate the constraint we took out, then we know this optimum is equal to the optimum for all of these constraints, the capital H set. Okay, so we just output that optimum. And otherwise, if the optimum of this thing over here does violate little h, then we're going to project all of these constraints onto little h's boundary, and then get a one-dimensional LP, which we can then solve. Okay, so now I need to tell you what this projection thing means, right? And what the boundary of h is, and then also like what this one-dimensional LP is. Okay. So, so given a constraint h, okay, now we know that these constraints are basically represented by a line and then everything to one side of the line, okay, either above or below the line. Okay, so the boundary of this constraint is simply the boundary of this region over here. Okay, so it's just this line over here, right, without all of the stuff beneath it. Okay, so it's simply the line which defines the constraint. That's the boundary, okay? We're going to use this notation, this del of h over here. Okay, so now, suppose, in the previous algorithm, the key step was to find the optimum value, this b of capital H minus a certain constraint h. Okay, and now suppose this optimum value actually violates this constraint h. Okay, then what that tells us is that the optimum value of b of h must lie on the boundary of h. Okay, it must lie on this thing. Okay, so for example, if previously we have this set of constraints, okay, well, the optimum for this set of constraints is going to be this point over here. Okay. However, if we add an additional constraint, right? So this set of constraints here, this is going to be b of h minus h. Okay, right, this red point over here. Okay, And now if we add another constraint, this little h over here, then you see that this point is actually going to violate the new little h constraint, right? Because little h says that we need to be on this side. Okay. But then what we know is that the optimum of b of h has to lie on this little h line. Okay, because so for example, once you add in this little h line, right, then we're trying to find the highest point possible, right? So that's what the sorry, let me erase this. So we're trying to find the highest point possible, right? And you see that after you add in this this constraint h, what we're trying to do is we still want to move in this direction as much as possible. Okay, so currently this red point here is sort of too high. Okay, it lies outside of h. Okay, so then we need to shift this point downwards, but you want to shift it as little as possible until it just satisfies h. Okay, and so that means that you want to put the new point over here. Okay, so this is going to be the optimum. And you see that this optimum lies on the boundary of h. Okay, yeah, so b of h must lie on the boundary of little h. Okay, so then the question becomes, where does it lie on the boundary of little h? Okay, and to answer this, what we're going to do is we're going to take all of these constraints, okay, these constraints other than little h, and we're going to project them onto the boundary of little h. Okay, so the boundary of little h is just this black line over here. Okay, so we're going to project all of the other constraints onto this black line over here. And what does it mean to project? Well, for example, if we take this constraint over here, okay, so when you project this constraint onto the boundary of h, then what you need to do is, well, this constraint says that we can consider all the points on this side. Okay, so if you intersect, this region over here with this line that defines h, then what you're going to get is that we see that we can consider, we're not allowed to consider any points, we're not allowed to consider any points in this region anymore, right? Because they all violate this constraint over here. Okay, so we need to remove all of these points, but we are still allowed to consider all the points down here. Okay, so when you project this constraint onto little h, then what you are going to get is this line over here. Okay, oops. All right, now you can take another constraint and then project it onto this line over here. So for example, if you take this constraint, right, and then you project it onto this line, well, this constraint says that we need to lie actually, be somewhere, in this region. Okay, so for example, all of these points violate this constraint, okay, because they're above that region. So we need to remove all of those points. Okay, so then if you do that, you see that we're going to go from the current, we're going to go from this line, and then we're going to chop off a little bit. We're going to chop off this part. Okay, right, and then likewise, you're going to project this constraint, okay, onto onto this remainder for h. Okay, so this is the remaining portion of h over here. Okay, and when you project this constraint onto this remaining portion, that means that we have to actually chop off this part over here. Okay, so if you do that, right? Okay, so sorry, I guess I use this constraint first. Okay, so this constraint says that, we need to be above this point over here. Okay, so we need to chop off all of these points over here. Okay, so if you do that, you see that we're going to chop off all of those points, right? And then finally we have one last constraint, and then this one says that we need to chop off all of these points over here. Okay, and so then what we're left with is we're just left with this line h. Okay, so actually I should take out this purple part, okay, because the thing that we're left with is we know the optimum is going to lie on the boundary of h. Okay, so it's just this line portion of h without the half plane on the right side. Okay, so then this line segment over here, right, between this point and that point, okay, well, this is going to be a one-dimensional LP, okay, because it says that, we need to be beneath this point and then above that point, okay, and we can be anywhere within that region, okay? And then we want to find the sort of the highest point possible in this line segment. Okay, so that's another linear program, except for it's just a one-dimensional linear program on this line segment. Okay, and so optimizing that linear program is of course easy, okay, because all you need to do is you just take one end of this, okay, either the left hand or the right end, and in this case we're going to take the right hand side of this, okay, and that's the optimum. Okay, right, so if we go back to this in the beginning, right, so then once you add in h, you're going to project all of these other constraints onto this line which defines h, and then after that we're going to be left with this segment. Sorry, let me redraw this. We're going to be left with this segment over here, right? This is a one-dimensional LP. We're going to optimize this, and then we're going to find that the optimum is at the the top half, at the top side of this. Okay, so yeah. Okay, so that's the algorithm. So now we see how the algorithm works, and so hopefully I convinced you that it's correct. And so the next thing we're going to do is analyze the complexity of this algorithm. Okay, so let's let T of n be the expected time to solve this two-dimensional LP when there are n constraints. Okay, so it's a randomized algorithm, so we're just going to look at the expected time. Okay, then what you have, so then you have this this equation for the running time. Okay, and the reason for this is because in order to solve this LP with n constraints, what we had to do was we had to first of all, so we randomly removed one of these constraints, little h. Okay, and then you recursively solve the problem with that constraint taken out. So then there are m minus 1 constraints. Okay, so therefore it's going to be T of m minus 1 to recursively find the optimum for this one. Okay, and then next you had to check whether this the optimum this optimum over here actually violated the constraint that you took out. Okay, so that just involves taking like a dot product. So that can be done in constant time. Okay, because we're in 2 dimensions. And then yeah, and then we said that there's actually a 2 in n probability, okay, that the optimum violates h, because there are only 2 tight constraints that define the optimum, okay, that define the true optimum for b of h, okay, and the probability that we picked little h to be one of those tight constraints is just 2 divided by n. Okay, and if we picked one of those 2 tight constraints, and then the optimum of this thing violates h, then we have to do this projection thing. We have to project all of the constraints onto this h, okay, onto the boundary of h. Okay, and this takes order n time because we have n constraints. Okay, we need to project all these n constraints onto the boundary of h. So that's where this order n comes from, right? So we have a 2 divided by n probability we have to do this. And then finally, after you do this projection, you have to solve this. We're left with a one-dimensional LP, okay? And then you have to solve this, but because the 1D LP is just a line segment, then you can solve this in constant time. Okay, so therefore we have this equation for the expected time complexity of the 2D LP. Okay, so you can actually solve this. So I'm not going to do this, but the solution to this equation is going to come out that T of n is going to be order of n. And so that means that you can solve a 2-dimensional LP with n constraints in expected linear time. Okay, so now we're going to generalize this problem a bit. So first of all, we ignored some special cases in the previous algorithm. Okay, so these are like corner cases. Okay, so for simplicity, we ignored a few of these cases. So one of these cases is that the LP that we have is actually infeasible. Okay, so infeasible means that there are no points that can satisfy all of the constraints. Okay, so for example, if one of your constraints is x1, right, so the variable x1 is larger than 1, and then you have another constraint x1 is less than 0. Okay, well, there are no points that can satisfy both constraints. Okay, another way to see this is, if you have, geometrically, if you have these constraints. Okay, so for example, this line over here means that we need to take all the points which are above this line. Okay, and then this other one means that we need to take all the points which are over here, and then we need to take all the points which are over here. Okay, Well, you see that there are no points which satisfy all three constraints simultaneously. Okay, so if you have these constraints, then your LP is infeasible. So we ignore that case. Okay. Another case we ignored was you could have a LP where the optimum is actually infinite. Okay. So for example, if we're trying to move in this direction over here, right? We're trying to find the farthest extreme point in that direction. Well, if your LP looks like this, okay, so that this side just goes on forever, okay, well then the optimum is going to be infinite. Okay. So so this is an explicit example where the optimum is infinite. Okay, and then finally, you could have a situation where you don't have an extreme point that satisfies your that maximizes your LP. Okay, rather you have an extreme edge which maximizes your LP. Okay, so for example, if we're trying to find the highest possible point, then if these are our constraints, then all of these points along this top edge are going to optimize this objective function, this C objective function. Okay. All right, so then we have these three different cases, corner cases, and it's actually possible to pre-process your LP in order to check whether you have any of these special cases. Okay, so therefore we're just going to assume that for the previous algorithm, the first thing we do was actually to check for these corner cases. Okay, and then if we do not have any of those corner cases, then we can use that previous algorithm. Okay, so then, yeah, so then next, so previously we talked about a two-dimensional LP, right? So we had two variables, the wheat and barley variables, okay? But you can actually consider higher dimensional LPs where you have, more variables, okay? Maybe you have like rice or something, okay? So you want to decide how much wheat, barley, and rice to plant, okay? So, so in general, we could have D of these variables that are involved in the objective function, okay? So now when that happens, so when we had two variables, then all of our constraints were lines, right? Were given by lines, okay? But if we're in higher dimensions, then these lines actually become planes, okay? And then the set of points which satisfy one of these constraints is going to be all of the points which are on one side of a plane. And this is going to be called a half space. Okay, so as an example, suppose you have, and then we have multiple ones of these constraints. And so what we need to do is to take all of these half spaces, right? So for each constraint, we form a half space, and then we need to satisfy all of the constraints. So then we're going to take the intersection of all of these half spaces. Okay, and so the intersection of these half spaces is going to give us a feasible region, and the feasible region is going to be all of the points which satisfy all the constraints. Okay, so for example here, right, we have I guess two constraints. So we have this constraint over here, right? So this is given by a plane, right? So for example, the plane might be something like x plus y plus z equals 1. Okay, and then if we want everything which is sort of facing away from us. Okay, so those would all be all the points where x plus y plus z is less than or equal to 1. Okay, and then we had, so that's one of these constraints. And then the other constraint would be, like a plane over here. Okay, so that's where this thing comes from, right? And then this would be, y is less than some value. Okay, so the intersection of these two constraints is going to give us this feasible region over here. Oh, and then we have some additional constraints where, for example, x, y, and z are all going to be at least 0 over here. Okay, so if you take all of these constraints and you intersect them, then you're going to get everything which is the sort of the solid shape. Okay, everything which is inside of the solid shape, that's going to be your feasible region. And this feasible region is actually you can show that it's going to be convex. Because you're intersecting a bunch of half spaces, and each half space is convex, so all these intersections are going to become convex. And this convex region is actually called a polytope. Okay, and so just like in the 2D case, the optimum solution, okay, the one that maximizes the objective, that that was at one of the extreme points of the 2D feasible region. Okay, so in general, in higher dimensions, the optimum point is going to be at one of the corners of the polytope. Okay, so for example, if we're trying to maximize cost in this region, then let's see. So let's try to draw it like this. Okay, then the optimum is going to be at this point over here. Okay, so if this is your objective function, then you want to push out a plane as far as possible in that direction, and so the optimum is going to be at this corner point over here. And this corner point, since we're in d dimensions, this is going to be the intersection of d of these half spaces, right? Because in order to form a point in d dimensions, you need to take d planes and intersect them, and that's going to give you a unique point. And then the objective function, I had a c over here. Okay, yeah, so this objective function c, right, this is going to define a direction. And then we're going to take a plane which is perpendicular to the c direction, and we're going to keep shifting it until it stops touching this feasible region, right? And that's the extreme point, which gives us the optimum. Okay. So the point of all this is that the extreme point is going to lie at the intersection of d half spaces. Okay, so in 2D, it's going to be at the intersection of two half spaces, and in general, it's going to be at the intersection of d half spaces. Okay. Yeah. Okay. So one more thing to say about this is that these polytopes can actually be very complicated. Okay. So this polytope, only has a few faces. Okay. But in general, if you have, let's say, n constraints, you could actually have an exponential number of faces for these, an exponential number of these extreme points. Okay, for the polytope, which is the intersection of all those constraints. Okay, yeah. So in general, it could have a very complicated shape like this. Okay, so now we're going to take the previous 2D linear program algorithm, and then we're going to generalize it to d dimensions. Okay, so the algorithm is going to work like this. So in d dimensions, if we only have d constraints, okay, then these constraints are only going to intersect at a single point. Okay, and so that's going to be the optimum, and so we're just going to output that as the solution to this LP. Okay, we're going to output the intersection of these d constraints. Okay, otherwise, we're going to do as before, we're going to try to find these redundant constraints. Okay, and because we don't know which constraints are redundant, we're just going to pick a random constraint, a little h. And then we're going to recursively find the optimum solution after you take little h out of the set of constraints. Okay? And then again, if this optimum does not violate this little h here, okay, then this optimum is actually equal to the optimum of all of the constraints. So in that case, we can simply output this optimum. Okay. And otherwise, this optimum is going to violate h. Okay, it's going to lie on the wrong side of h. And in that case, we need to take all of these other constraints, and we're going to, again, project them onto the boundary of h. Okay, so just like we took previously, we took in 2D, we took a bunch of these, half planes, right? And we projected them onto this boundary, which was simply a line, right? So now we're going to take these half spaces, and we're going to project them onto h's boundary, which is now a plane. Okay, so h's boundary is going to be a d-1 dimensional plane, and we're going to take all of these half spaces and project it onto this d-1 dimensional plane. And then, so that's going to give us another LP. Okay, it's going to be a d-1 dimensional LP, because each of these things is going to be so h's boundary was initially just a d-1 dimensional plane, and then we add on top of that all of these other constraints, right? So the projection basically corresponds to adding a constraint. Okay, so this is going to form a d-1 dimensional linear program. Okay, and then finally, we're going to recursively solve this d-1 dimensional linear program, okay, which comes from all of these projections. Okay, and then what we know is that the optimum solution, so if the optimum does violate h, okay, then the optimum solution actually has to lie on the boundary of h. Okay, and furthermore, that optimum is also subject to all of these conditions. Okay, so therefore, if we take the boundary of H and then we add on top of that all of these additional restrictions, right? So we use these projections to add these constraints, and then if we solve that d minus 1 dimensional LP, then that's going to give us the optimum solution for the original LP, B of H. Okay, so that's the algorithm. So now let's analyze the complexity of the algorithm. Okay, so the complexity is going to depend on two variables, the number of constraints and the dimension. Okay, so n is going to be the number of constraints, and then d is the dimension. So what we have is that, we have this equation over here. Okay, so the reason we have this is because, well, this part over here, okay, remember that we needed to recursively find the optimum for, h minus little h. Okay, so then here there are m minus 1 constraints, right? But we're still in d dimensions. So therefore the amount of time is going to be t of m minus 1 comma d. Okay, and then after that, we need to check whether this optimum is going to violate h. Okay, and now this is going to take order d time because you need to take a d-dimensional dot product. Okay, so remember that the optimum is defined by by d of these constraints. So they're d-tight constraints in a d-dimensional linear program. Okay, so the probability that this little h, this random constraint that we picked, was actually one of these tight constraints is going to be d divided by n. Okay, and if we picked h to be one of these tight constraints, then the optimum is going to violate h. So there's a d divided by n probability the optimum violates h. Okay, so that's where this d divided by n comes from. And if the optimum, right, if this optimum violates h, then we're going to have to do these projections, right, of this stuff onto the boundary of h. Okay, so there are m minus 1 constraints in this set, right, and projecting each one of them onto the boundary of h is going to take d time for each one of these constraints. Okay, so altogether it's going to take d times n time to do all of these projections. And then furthermore, once you do that, we're going to end up with a d minus 1 dimensional LP, right? Because this LP is only going to lie on the boundary of h, okay, which has d minus 1 dimensions. And it's also going to have one less constraint because we took out the h constraint. Okay, so then we need to solve this d minus 1 dimensional LP. So the final step over here is this is going to be a d minus 1 dimensional LP with n minus 1 constraints. Okay, and it's going to take this much time to solve it. Okay, so those are all the terms in this equation over here. And so if you solve this equation, then you're going to find that this time complexity here is going to solve to basically d factorial times n. Okay, so this randomized algorithm can solve an LP, and the amount of time is going to be linear in the number of constraints, but it's exponential in the number of dimensions. Okay, so that's our randomized algorithm for solving these LPs. So I just want to say a few more things about linear programming because because it's such an important area. Okay, so now we phrase these linear programs as these constraints and then this linear objective. Okay, so you can write this a bit more systematically using matrix notation. Okay, so we're trying to optimize this. We're trying to maximize 3w plus 4b. Okay, so you can write this as the dot product of two vectors, and then you can also write these constraints as the product between a matrix and a vector. Okay, so I've done that over here, right? And in general, these matrices and these vectors are going to have these dimensions. And so what we're doing is we're taking, for example, if we have n of these variables, okay, so then we're taking the dot product between two n-dimensional vectors, okay, and then if you have m constraints, right, then A here is going to be an m by m matrix, okay, and this needs to be less than so then these values on the right here, they're given by this B matrix, Okay, this is also going to be a m-dimensional B matrix. I'm sorry, B vector. Okay, so that's the first thing. Second is that, so we talked about this randomized algorithm, but there are actually quite a number of algorithms for solving linear programs. Okay, so one of the earliest algorithms is called the simplex algorithm. So this was invented by Danzig way back in the 1940s. So we know that so Danzig also knew that the optimum is going to lie at one of these corners of the polytope, right? The extreme points of the polytope. So then for the simplex algorithm, the way that you find the corner, which gives you the optimum, is that you're going to walk along the boundary of the polytope. Okay, so you're going to start at some corner of the polytope. So for example, maybe you're going to start at this corner of the polytope. Okay, so this is not the optimum. Okay, but then this point is going to lie on one of the faces of the polytope. And so therefore you can go from this point to one of the neighboring points on this face. Okay, so you're going to go, let's say, over here, right? And then from here, this point also lies on, from here you're going to go to another corner of this face, maybe over here, right? And now this point lies on this face over here, right? And then so you can go to another corner on this face. Okay, so the simplex algorithm is just gonna move along the faces of these of the overall polytope, and then it's always going to move in the direction that improves the objective function. Okay, so eventually it's going to get to the optimum, and once you're at the optimum, then there's no way to move to another corner point such that your objective still improves. Okay, so then once you get to this point, you're going to find that all of these other neighboring corners, right, they're not going to have a better objective. And so at that point, you know that you found the optimal solution. Okay, so that's the simplex algorithm in a nutshell. The problem is that in the worst case, we said that these polytopes can be very complicated, and they can actually have an exponential number of these vertices, of these extreme points. Okay, so the the running time of this simplex algorithm depends on how many vertices this polytope has. Okay, and so the running time in the worst case can be exponential. However, in practice, people have observed that you hardly ever get these worst case examples when you use the simplex algorithm in practice. Okay, so in practice, we still use this algorithm, and it usually works very fast. Okay, but if we want to guarantee that we can solve this linear program in polynomial time, then so there was a polynomial time algorithm to solve LP, which was discovered in 1979 by this person Khachiyan here. Okay, and this is a very famous algorithm called the ellipsoid method. Okay, so basically, it's going to find these ellipsoids, right? So these sort of squashed spheres. Okay, and then these squashed spheres are always going to enclose the optimum. Okay, and then so it's going to keep looking for these smaller and smaller spheres, smaller and smaller ellipsoids. Okay, until you get to a very small ellipsoid which encloses the optimum, and then that is the optimum. And then Khachiyan showed that this method actually terminates in polynomial time. However, this algorithm, if you use it in practice, it's actually quite slow. Okay, so even though in theory it's better than the simplex algorithm, it's faster than simplex, in practice it's actually much slower. However, there are also practical algorithms which can terminate in polynomial time. So Carmarker found this algorithm, or rather this class of algorithms called interior point methods. Okay, and so these can optimize this linear program in polynomial time, and they actually work fast in practice. And so they're used quite often in practice also. Okay, so there are actually a number of applications of linear programming. We're going to see some applications later. Okay, in fact, linear programming is one of the most important algorithms that we have. Okay, just like things like FFT and sorting. Okay, so LP is a very fundamental algorithm, and so in fact, when it was first discovered that LPs are actually solvable in polynomial time, right? So remember that this person, Khachiyan, right? So he's actually a computer scientist from the Soviet Union. So when he first discovered this ellipsoid algorithm, this was such a big deal that it even made the New York Times. Okay, so this is from 1979 in the New York Times. Okay, so just to give you one sample application of linear programming, okay, we can actually use this to solve network flow. So the way we do this is that in the network flow, so we have these edges in network flow, right? And for each of these edges, we're going to associate this flow value, okay? So for each edge UV, okay, we're going to let f of UV be the amount of flow from U to V in a solution to a network flow. And so then if we want to solve this, if we want to solve a max flow problem, then what we're trying to do is to push as much flow out of a source node as possible. Okay, so we want to say that for all of the flow that's coming out of the source node to any other vertex, right? We want to sum all of those, and we want to make this as large as possible. So this is our objective, right? And this is a linear objective, okay? Because all of these things are simply numbers, right? Okay, now these numbers are subject to certain constraints. So for example, the amount of flow from U to V can be no more than the capacity from U to V. Okay, so we have all of these, so we have these constraints for all pairs of nodes U and V. Okay. Furthermore, the amount of flow in one direction, right, from U to V is going to be opposite the amount of flow from V to U, right? And then finally, we have this flow conservation requirement. Oh, so maybe I should label these. So we have the flow conservation requirement, which is saying that if you add up all of the flow that is coming into U and also going out of U, okay, then this has to add up to 0. Okay, and this is true for all vertices except for the source node and the sink node. Okay, so for example, if you have a node U over here, right, and then let's say that you have amount of flow, let's say 3 going into here. Okay, and then so then you need to have some amount of flow going out of U, right? So then here you have a vertex, let's call this V1, and then you have some flow going to V2 and then maybe going to V3. Okay, and so let's say that there's an amount of flow 1 over here, an amount of flow 2 over here. Okay, all right. So then that would mean that the flow from V to U, right? So this flow, the top flow would be -1, right? If the flow from U to V, V2 is +1, then the flow from V2 to U is going to be -1. Okay, and likewise, should draw it this way, right? Then the flow from V3 back to U would be -2 over here. Okay, so then what you see is that if you take U and then you add up the flow from U to all of its neighbors, okay, or in fact to all of the nodes in the network, okay, including its neighbors, then this has to add up to 0. Okay, for example, U to V1 is 3, but then U to V2 is -1, and then U to V3 is -2. So then if you add all these up, you get that this is 0. And this is the only way to conserve the flow at U. Okay, we need to have this for all of these nodes V other than the source and the sink. Okay, so then these constraints are actually all of the constraints we need for the max flow problem. Okay, and all of these things are linear constraints, right? Because all of these things are just they're linear constraints. And so we can actually solve this using linear programming. So therefore, linear programming can help us solve network flow. Okay, and in fact, linear programming is much more general than network flow. However, if we actually have a max flow problem, then probably you do not want to phrase it as a linear program and then use a linear programming solution. Because these algorithms that we have for linear programming, right, like the interior point method or the simplex method, even though they're polynomial time, they're still somewhat slow. Okay, so we have actually more efficient algorithms to directly solve these max flow algorithms rather than using these more general LP algorithms. Okay, so this is all I'm going to say about this linear programming algorithm. And this is also the end of our chapter on randomized algorithms. And so next, we're going to move on to a new chapter, which is going to be talking about approximation algorithms. Okay, and we're going to cover this problem called set cover. Okay, so first of all, let me introduce approximation algorithms. Okay, so up to now, most of our algorithms have been exact algorithms, meaning that they find an optimal solution to a problem. Okay. However, we know that there are many problems for which we cannot find an optimal solution. Right? For example, NP-complete problems. Right? We cannot find optimal solutions to NP-complete problems, as far as we know. Nevertheless, these problems come up in practice all the time. Okay, and so we need to do something with them. Right? We need to give some sort of solution to these problems. And so what we can do is, if we know that we can't find the optimal solution, then let's just go for an approximately optimal solution. Okay, a solution that's as good as we can make it. And so, so that's what approximation algorithms are. Okay, they don't find the optimal solution, but rather they find an approximately optimal solution. Okay, so to be more precise about this, suppose first of all that we have a maximization problem. Okay, so let's let X be some sort of maximization problem. Okay, and let's let A be an algorithm for solving X. Okay, now we're going to pick a constant alpha, which can be anything larger than 1. Okay, then we're going to say A is an alpha approximation algorithm for this problem X if A always returns an answer which is at least 1 divided by alpha times the optimal. Okay, so X is like a maximization problem. Okay, so for example, if X is max flow, then you say that A is a 2 approximation algorithm if it always returns a flow which is at least 1/2, 1 divided by alpha, the optimal. Okay, and we want alpha to be as close to 1 as possible. Okay, because the closer it is to 1, the closer this this approximate max flow is to the actual max flow. Okay, in fact, if alpha equaled 1, right, then this algorithm would give you the optimum solution. Okay, so this is for maximization problems where you want the answer to be at least 1 divided by alpha times the optimal. And if you look at minimization problems, then we're going to say that A is an alpha approximation if it always returns an answer which is at most alpha times larger than the optimal, right? Because here we're trying to make X as small as possible. Okay, so we want to make sure that the answer we get from A is not too much larger than this small answer that we want. So for example, if X is min cut here, okay, so that's a minimization problem, then A is going to be a 2 approximate algorithm if it always returns a cut which is at most 2 times the size of the smallest cut. Okay, so that's what and again, we want alpha to be as close to 1 as possible. All right, so those are the approximation algorithms. That's what it means to give an approximation algorithm. And so the first algorithm we're going to look at is an algorithm for a problem called coverings. Okay, or actually a specific type of covering. Okay, but let's first talk about in general what covering problems are. So to motivate this, suppose you have like a set of teachers, okay, and then each teacher can teach a certain set of classes. Okay, so you can represent this as follows. Okay, so then here these points are representing the classes. Okay, so we have like 12 classes here, and then each of these circles over here, or this shape over here, this represents the set of classes that a teacher can teach. Okay, so for example, teacher S1 here can teach these 6 classes. Okay, teacher S2 can teach these 4 classes. All right, and the entire set of classes, okay, all of these points is going to be called X. And now what we want to do is to pick the minimum set of teachers who can teach all of the classes. Okay, we want to make sure that all of these classes can be taught by somebody. So we want to pick a set of teachers to teach all of the classes, but we want to hire as few teachers as possible So we want to pick the minimum set of teachers to teach all the classes. Okay. In other words, if T is the set of teachers that we pick, okay, then we want the union over all of these teachers. Okay, so for each of these teachers, I, that teacher can teach this set S sub I of classes. And we want the union of all of these SIs to be equal to X, which is the set of all classes. And then we also want T to be as small as possible. Okay, so this is called a set cover because we're using these sets, right, these S1, S2, and so on, we're using these sets to cover all of these points. Okay, so yeah, and this is a minimization problem. So it's the minimum set cover problem. Okay, so a bit more formally, so our input to this set covering problem is going to be a collection, a set of sets. Okay, a collection of sets. Okay, let's call that F. And then each set, so these sets are also going to have costs. Okay, so like maybe the teachers have different salaries, right? So we want to pick like the cheapest set of teachers, right? In terms of their total salary, we want to pick the cheapest set of teachers who can teach all the classes. Okay, so each of these sets has a cost, right? And the union of all of these sets, okay, is going to contain all of the points. Okay, so if we hire all the teachers, then we can definitely teach all the classes. Okay, we're gonna call these points X. And now we want to pick a subset of these sets. Okay, we want to pick a subset G whose union is going to be equal to X. And our goal is to minimize the total cost of the sets in G. Okay. Yeah, so for example, if all of these sets here have the same cost, then if we pick S3, 4, and 5, okay, so if we pick this one, and then this one, right, then we can cover all of these points. Okay, now this set cover, this minimum set cover problem, this is an NP-complete problem. Okay, so therefore we can't really hope to find the optimal, the minimum total cost for covering this set. Okay, but instead we're going to look at an approximation algorithm, and this algorithm is going to have this approximation factor. Okay, the natural log of n. So this means that for so here n is going to be the size of x. Okay, so yeah, so n is the total number of classes that we have. Okay, and so oh right, I wrote that. Okay, so this means that the larger x is, right, then the worse this approximation factor. Okay, so for example, if x is like yeah, so because this function here is actually growing as a function of n. Okay, so if x is really large, right, then we're going to get a somewhat poor approximation. Okay. All right, so the way this algorithm works is that it's basically a greedy algorithm. Okay, and the idea for the greedy algorithm is to choose sets which cover the points in the cheapest way. So what I mean by that is, suppose you have a set, right, and it's got a cost of C. Okay, and now this, let's say that the set can actually cover m of these points. Okay, so for example, if you pick this S5 here, it can cover 4 points. Okay, then what you want is you want the set to be cheap, right? So you want C to be small, and then you also, because you're trying to cover all the points, you want m to be large. Okay, and the way we're going to measure how good this set is we're going to look at the average cost to covering a point. Okay, because even if C here is rather large, but if this set can cover like a huge number of points, then it's still a worthwhile set to use. Okay, so the metric we're going to use to like measure how good a set is we're just going to take C divided by m. Okay, so that's the average cost for this set to cover each element. And then we're going to use a greedy heuristic, meaning that we're going to pick the set which has the smallest C divided by m value. Okay, so C divided by m is the average cost for a set to cover an element, and we're going to pick the cheapest such set. And then yeah, so the algorithm is going to pick that set, And then after that, it's going to remove all of the points that the set covers. Okay, and so that's going to leave us with some remaining points, right? And then also some remaining sets. Okay, and out of these remaining sets and remaining points, we're again going to pick the set that can cover these remaining points in the cheapest way possible. Okay, so the algorithm for doing this is is as follows. Okay, so initially you have a set of sets. The entire set of the collection of sets is called F, right? And the set of points is called X. Okay, and then each set is going to have a cost, which is cost of S. Okay, and then U here is going to be so as we run this algorithm, we're going to cover more and more nodes, right? More and more points, okay, or elements. And so U here is going to be the set of uncovered elements, okay, the elements that we still have not covered yet. And then C here is going to be the set of sets that we select, okay, so it's going to be the cover, the collection of sets that we select to cover all of X. Okay, so initially all of the points are uncovered, okay, and then we haven't selected any sets yet. And then what we're going to do is run a while loop. So while there are still any uncovered elements, okay, so while we have not produced a complete set cover yet, then we're going to choose a set among the remaining sets. Okay, so we've already chosen these sets, right? The C here is a set of sets we've already chosen, so we can't choose those again, okay? But we can choose any other set, right? And the set we're going to use is that we're trying to minimize the cost of this set, right, divided by the number of elements that it covers, okay? But we only care about the uncovered elements that it can cover, right? So so for example, maybe you have the set over here, right? So maybe it covers like a bunch of elements, okay? But maybe many of these elements have already been covered by the rest of C, okay? In that case, this set can actually only cover 2 additional elements, okay? So we're going to look at the cost of this set divided by the number of new elements, uncovered elements that it can cover. And we're going to pick the cheapest among those sets, okay? And then we're going to add that set to our cover, right? And then also, now we've covered all of these points in S, so we're going to take those points out of the uncovered set, okay? And you keep doing this until you've covered all of the sets, all of the points, okay? And then you output this cover C. Okay, so that's a simple algorithm, and clearly it's a polynomial time algorithm. We're not going to compute the exact complexity, but it's very cheap to run this algorithm. And so now what we need to prove is that this algorithm, first of all, is correct, meaning that it actually does output a set cover, right? And then second of all, we need to put a bound on the cost of this algorithm, right? So in the end, this C here is going to have some sort of cost, okay? And we want to compare this cost that the algorithm output to the minimum possible cost. And you want to show that C is not too large. Okay, so in terms of showing this is correct, well, first of all, the output of this algorithm is definitely a set cover, okay? The C set here, right, definitely covers all of the points in X, okay? And that's just because while we have any uncovered points, we're going to keep picking additional sets, right? And then we know that all of these sets, if you take them together, you can cover X, okay? So in the worst case, we're going to take all of the sets in this entire collection, okay? But in any case, when we stop, we definitely cover all of the points in X. Okay, so the next thing is to show the approximation ratio for this algorithm, okay? It's to show that the cost of the set C is not too much larger than the minimum possible cost. And so here, we said that the approximation ratio is going to be log n, okay, natural log of n. And the way this comes about is because natural log of n is approximately equal to the sum of this harmonic series, okay? 1 plus a half plus a third plus a quarter, and so on, okay? And what we're going to show is that if the minimum cost of a set cover is v, okay, then the set cover that we compute using the previous algorithm is going to be at most natural log of n times v. Okay, so so the basic idea for this proof is to bound the cost of the set cover. So bound the average cost of the set cover that we have. Okay, so the cover is C, right? So we're going to bound the average cost that C incurs on each element, right? So in the end, we cover all of the elements. Okay, and we're somehow going to define this notion of average cost to cover each element. And then we're going to show that this leads to some sort of sum of a harmonic series. And then from that, we'll get this log and approximation ratio. Okay, so to do this, what we're going to do is we're going to order the sets in C by when they were added to C. Okay, so remember that this algorithm, right, as you run this algorithm, it's going to add more and more sets. Okay, and the basic idea is that so whenever you add a set, right, we're always trying to choose a set which minimizes this cost. Okay, so in the beginning, you're allowed to choose any set from F. Okay, so in the beginning, we can actually get a set S, which really has a very small average cost here, right? So this is the average cost to cover an element, an uncovered element, right? Because this is a set of uncovered elements, and that's the cost of the set. So this is the cost to cover an uncovered element. And in the beginning, because you're allowed to choose any set you want, then you can find a very cheap set, okay, in terms of average cost. Okay. But the point is that as we run this algorithm, then we've used more and more of these sets. Okay, so the sets we're still allowed to use, that's shrinking. Okay, and so that means that because we're more constrained in terms of which sets we can use, then we're no longer able to find these very cheap sets anymore. Okay, so these average costs are actually going to increase as we run this algorithm for more and more iterations. Okay, so again, the initial sets that we pick, these initial S are going to be have lower average cost, and the average cost is going to increase. Okay, and so now what we're going to do is we're going to take all of these sets and we're going to order them in the order that we added them. Okay, right. So the first set that we use is going to be S1, right, and then the next set we're going to call that S2, and so on. Okay. So yeah, so this is going to be the order that we selected these sets. Okay, and let's say that in total you select M sets. Okay, so then the cost of the set cover that we have is simply equal to the cost of the sum of the costs of all of these sets. Okay, so for I equals 1 up to M, right? Okay, so now we order the sets this way. Okay, but let's also order the elements which these sets cover in the same way. Okay, so for example, if if this is S1, okay, so let's say it covers these elements, E1, E2, E3. Okay, so then we're going to have E1, E2, E3, and let's say that next you select set S2. Okay, and so so this is going to be set S1 over here. Okay, and then let's say that set S2 is going to cover two elements. Okay, it's going to cover E3 and E4. Okay, so then E4 is going to be the sort of the next element that's covered. Okay, and then let's say that you have a set S3 over here, and it's going to cover E5, E6, and let's say E7. Okay, so you see that we're going to order the elements in the same order as the sets which contain these elements. Okay, yeah, so the first few E's are contained in S1, right? And then S2 contains the next few E's, few elements, and so on. Okay, now what we know is that because in the end, if we take all of these sets, okay, if we take S1 up to Sm, then this is going to be a set cover, and so that means that all of these sets are going to be, all of these elements are going to be covered. Okay, so so that means that we can cover all of these elements E1 up to En, using these sets. Okay, now let's let Ni be the number of new elements that Si covers. Okay, so for example, S1, right? Sorry, did I? So N1 here would be equal to 3. right? Because S1 covered 3 new elements. Okay, and then S2, well, it covers 2 elements, but only one of them is new. Okay, only E4 is new. So therefore, N2 is going to be 1. Okay, and then S3 is going to cover 3 new elements. Okay, so N3 is going to be 3. Okay, so that's how we're going to define these NIs. Okay, now we're going to take the cost of SI, right, and then we're going to divide it evenly among the new elements that it covers. Okay, so we're going to take this cost of SI and divide it by NI. Okay, so again here, we're going to take the cost of S1 and divide it by 3. We're going to take the cost of S2 and divide it by 1. Okay, and then cost of S3 divided by 3. Okay, now we have this expression over here. Okay, so so suppose you want to add up the, suppose you define the cost of an element in this way. Okay, it's the cost of the set which first covered that element divided by the number of new elements that the set covered. Okay, so that's how you define this cost of E. And suppose you add up the cost of all of these elements, okay, for k equals 1 up to n. Okay, then what that equals is, well, each of these elements, so each of these sets Si, right, it covers ni new elements, right? And so and so all of these new elements which are being covered by Si, they have the same cost. Right, so for example, you know, S3 covered 3 elements. Okay, so all of these 3 guys, these 3 elements, have the same cost, which is equal to cost of S3 divided by 3. Okay, so therefore the sum of all of the cost of all the elements is equal to, well, we have this number of new elements covered by Si times the cost for those elements covered by Si. Okay, and this is equal to, and now if you just multiply this, right? So this is equal to the sum of all of these SIs, right? And and that's the total cost of the algorithm. Okay, so let's call that L. Okay, so so we have this expression over here, and now what we're going to do is we're going to bound the cost of each of these to cover for each of these elements, and we're going to show that this cost is going to be at most the optimum cost that, you know, the optimum cost for covering all of these elements, okay, produced by the optimum algorithm, divided by m minus k plus 1. Okay, so k is, so here we're talking about the kth element. Okay, so k is going to go from 1 to n, and we're going to, and you see that the cost to cover these elements is actually going to be increasing. Okay, initially for k equals 1, right, we have that the cost to cover E1 is at most going to be optimum divided by n. Okay, but as you make, for example, for k equals n over 2, okay, then, or sorry, for k equals n, let's say, for the final element that's being covered, okay, then all that this bound says is that the cost to cover the final nth element is going to be at most opt divided by 1. Okay, so, you know, so that's possibly a very large cost. Okay, but we're going to show this for every k from 1 to n. Okay, now if we can actually do this, if we can show this bound, okay, then we can actually prove the approximation ratio, because the total cost L is equal to the sum of all of these costs of all these elements, right? And then if each one of these is for the kth element, if that's at most the optimum cost divided by m minus k plus 1, right? Then we can just take this optimum out of over here, and then so then we're left with this sum over here, which is the sum of a harmonic series. Okay, and we know that the sum is going to be at most log of n. Okay, so therefore this L here is going to be at most log n times the optimum cost. Okay, and that shows that this algorithm is a log n approximation. So then the only thing we need to do is to show this bound over here. Okay, so the way we're going to show that is, now let's focus on some element ek, okay? And let's say that S sub j, okay? So let's say that ek was covered for the first time using the jth set, sj, Okay, so remember that we ordered these sets in the order that we selected the sets from the algorithm. Okay, so let's say that the jth set that we selected covers this element ek for the first time. Okay, now when you cover ek for the first time, then remember that we order these elements in the order that they were covered. And so when you were covering ek for the first time, then that means that all of these other elements beyond ek were still uncovered. Right, so we still haven't covered ek plus 1, ek plus 2, and so on. Okay? And now, however, if you look at the optimal cover, okay, so we're trying to compare our cover to the optimal cover. Now, we know that the optimal cover, of course, needs to cover all of these elements. Okay? And so let's let C1 up to Cm be the sets in an optimal cover which covered these elements, ek up to En. Okay. Okay. And for each one of these sets, let's say that, for example, C1 covered n1 prime number of elements from this set. Okay, so we're going to call this set U, and let's say that C1 covered n1 prime elements of U. Okay, and then we're going to define all of these ni primes this way. Okay, so nm prime is going to be the number of elements of U that Cm covered. Okay, now we're going to have several observations. So the first observation is that if you add up all of these m prime values, okay, this is going to add up to at least m minus k plus 1. And the reason is simply that, well, you know, these C1 up to Cm, they actually have to cover all of these elements, right? And they're m minus k plus 1 of these elements. Okay, so therefore, if you look at the number of elements that each one of these things cover, and then you add those up, that's got to be at least m minus k plus 1. Okay, so the second observation is that if you add up the costs of all of these sets, this is at most the optimum. Okay, and this is because these C1 up to Cm, right, they're the sets from an optimal cover which cover U. Okay, and so there could be additional sets in that optimal cover. Okay, so these C1 and up to Cm are just a subset of the optimal cover. And the optimal cover itself has cost opt. Okay, so then C1 up to Cm is going to have cost at most opt. Okay, so the third observation is that if you look at these C sets, okay, so none of them are among the first j minus 1 sets that we selected. Okay, so remember that we're looking at this element ek, and then the first time that it's covered by one of the sets that the algorithm selects is the jth iteration, right? It's this Sj set. Okay, so prior to this iteration, we selected sets S1 up to Sj minus 1. And what we're saying is that none of these C sets can be among the first j minus 1 sets we selected. Okay, and the reason is that if, let's say one of these sets, okay, let's say Ci, okay, is among one of the first j minus 1 sets that we selected. Okay, now we know that Ci is going to cover some of the elements of U. Okay, so it's going to cover some element of U. Okay, so where U are these elements over here. Okay, Ek up to En. Okay, so if C, let's say that Ci covers, let's say that Ci covers these elements. Okay, now if Ci is actually one of these sets, okay, S1 up to Sj minus 1, okay, then that means, so for example, let's say that J here is let's say that J equals 3. Okay, so what we're saying is that C1 up to Cm is not among S1 and S2. Okay, because if one of these C's was among S1 or S2, right, then let's say that Ci here, let's say that it equals S1, let's just say, okay, then Ci is covering these two elements, right, Ek plus 1 and Ek plus 2. But then that means that S1 covered Ek plus 1 and Ek plus 2. Okay, but we know that by the time we get to this S3 over here, we still have not covered any of these elements yet. Okay, so in particular, S1 cannot cover any of these elements, right? Because these elements were not covered even by the time we got to S3, right? And these elements are listed in the order that they were covered. Okay, so that means that none of these C's can be among the first J-1 sets that we selected. Okay, now the next observation is that among all of these sets, these C sets, okay, there must be one of these C sets such that if you take the cost of that set divided by the number of elements from U that it covers, okay, this is going to be at most opt divided by n minus k plus 1. Okay, and the reason is that suppose for contradiction that all of these CIs, okay, have this value larger than opt divided by n opt divided by m minus k plus 1. Okay, then what you have is that, well, we know that the sum of all of these C's is going to be at most opt. Okay, but then this is equal to to this expression over here. Okay, but if we assume that each one of these values here is going to be larger than opt divided by n minus k plus 1, right? Then we have this thing over here. Okay, well, now we can just take this part out. This is constant, right? And so so we're left with this, right? And now what we know is that the sum of all of these m prime I values, okay, so this is going to be at least m minus k plus 1, okay, because all of these C's together are going to cover these m minus k plus 1 uncovered elements. Okay, so now we get a contradiction, right? Because we end up saying that the opt is larger than the opt. Okay, so therefore there must be at least one of these CIs such that this average cost of CI, okay, this cost of CI divided by the number of elements that it covers, this has got to be at most opt divided by m minus k plus 1. Okay, so now we're almost done, because now what we can say is that the cost of Sj, okay, so remember that we're focusing on the on this Sj here. Okay, this Sj is the set which covered Ek for the first time. Okay, now what we can say is that the cost of Sj divided by the number of new elements that Sj covers, okay, is going to be at most this quantity. Okay, and this is because when we were choosing Sj, okay, the only sets you're not allowed to choose are the ones that we've already chosen, which are S1 up to Sj minus 1. Okay, all of the remaining sets we can choose. Okay, so Sj can be anything among anything which is not S1 up to Sj minus 1. Okay, and now what we said earlier was that all of these C sets, okay, these are not among S1 up to Sj minus 1. Okay, so therefore when you choose Sj, you're actually allowed to choose any of these C sets if you wanted to. Okay. And we also said that at least one of these C sets has this condition. Okay, the average cost for that C set is going to be at most this opt divided by m minus k plus 1 here. And now remember that we have the algorithm was greedy. Okay, so so we chose S with the minimum average cost. Okay, so we chose S in order to we chose our set Sj in order to minimize this cost of the set divided by the number of uncovered elements. Okay, and so therefore, since we're allowed to choose any of these C sets, okay, and there's at least one of these C sets where this cost is going to be no more than this quantity over here, then since we're choosing the minimum average set, then our average cost for the set Sj that we pick can be no more than the average cost for the Ci set, right, which is going to be no more than this value over here. Okay, and so therefore we have this statement over here. Okay, and now we know that this cost over here, right? Well, this is exactly equal to the cost of Ek. Okay, because Sj is the set which covered Ek for the first time. Okay, and the way we defined Ek was that you took this cost of Sj and then you divided by the number of uncovered elements. Okay. And so therefore we have that the cost of ek is going to be at most the opt divided by n minus k plus 1. Okay, and then as we said earlier, from this we can get the approximation ratio because the total cost is equal to the sum of all of these ek costs, right? And this is going to be, we showed that, this is going to be at most, oops, this cost over here, this sum over here, right? And this is at most log n times the optimum. Okay, so the cost for this algorithm is going to be at most log n times the optimum cost. And so therefore, this is a log n factor approximation algorithm. Okay, so that's all we have for this lecture. So next time, we're going to talk about some additional approximation algorithms. Okay, so see you guys next time.